So hello everyone, thank you, and I want to bring now something little different to the whole conversation we have had up to now about quantum. I want to bring in organic materials and show how they can be applicable for quantum applications and what's their main benefits. And so my talk will be about quantum light sources with a special focus on integrated photonics and quantum photonics. So just let's start to tackle first the photonics part, because there's a lot of transition with the same issues also for quantum photonics and quantum light sources. So in general, when we look at the state of integrated photonics, there exists like multitude of platforms that we can use to manufacture photonic chips. But the main issue is that there's not a single platform that can give us everything that we want into a single chip. For example, silicon photonics is one of the most established platforms, mainly due to high density of elements, low optical losses, high manufacturability yield, compatibility with CMOS systems. Very, very nice when we talk basically about passive structures. But when we transition to something active, that we want to have a laser source on chip, there's places, that's the place where silicon photonics start to lose their advantage, and basically we cannot find any other platform that would have high active properties and low optical losses. So what we do, we try to combine different elements. For example, we have a 3-5 laser, the lithium niobate modulator, silicon photonics, and so on. And now, if we look more to quantum photonics, it's the same issue. So again, if we look at quantum integrated photonics, we don't have a single platform that encompasses every element that we would need to create quantum chips. And there's a special vacuum in this table, which is single photon sources and coupled photon sources, which altogether we call quantum light sources. So for this talk, I will bring them together and tell what we are doing with them. And similarly, as laser was one of the key elements to really drive the development of photonics in general, I believe the quantum light sources, and efficient quantum light sources, is one of the cornerstones to really push quantum integrated photonics further. And the applications are many. Basically everything that, starting with quantum cryptography, quantum computing, quantum metrology, quantum internet, imaging. There's a lot of, all of these places can strongly benefit from efficient quantum light sources. And so this is something that we at Institute of Solid State Physics have recently started to work with. Again, I will take a bit of step back to classical photonics, because this is from where we come. For quite a couple of years, we have been working on a new initiative that we call polymer photonics. We want to establish a new polymer platform that could tackle a lot of issues that exist nowadays in photonics. Mainly, we have quite a nifty way how to go around the aspect that it's difficult to tune the properties of specific platforms, so that you want to have one elements with these low losses and somewhere you want to have inactive elements. We have a way how we can basically, using two material system where one defines the mechanical properties and the other one defines the active properties, we can tune different properties on the chip for specific elements, and we kind of can achieve a lot of functionalities in the same platform. We have simple fabrication techniques, which is quite essential if we really talk what now Europe is talking. We want to bring fabrication home. We want to be independent, and this is place where also this will be connected to quantum applications where we can use organic materials. We can talk about easy fabrication here in Europe and scalable. So it's not only the cost of the chip, but also the cost of the fab that we need to fabricate them. We don't want to push everyone else out. We want to play with them. So we are quite easy to integrate with a lot of other platforms, wide wavelength range applications, and low power. And so now we have started to take this platform and start look how we can apply it for quantum. And here, last year, we started a new twinning project in collaboration with Riga Technical University, as well as Trento and Troyes, to really bring and develop quantum photonics here in Latvia, with focus on quantum light sources, to learn from them regarding characterization from their experience to help to develop our own technology. And one of the great things already as we have started this project, we can see that although they have studied a lot regarding like different quantum light sources, polymers is something that they are encountering first time, so they can also learn a bit from us. So it's really an exchange of information and experience in both directions. So now I would like to just give you a brief introduction of what we are actually doing here, what's our vision about single photon sources and coupled photon sources, because those are the two main tasks we are tackling. So let's start with single photon sources. So as the name states, I think it's quite obvious we're basically talking about something that can emit a single photon at a time in a controllable way. And yeah. If we look at what's existing currently in the market, there are a lot of different applications, basically materials and sources that can be used. We have quantum dots, we have color centers, atomic ionic systems, and also what we are trying to work, we have organic molecules. There are a couple more, there could be mentioned even more parameters where we can compare them, but I picked these ones because I want to really stress out, because when we look at this issue, we don't look at it only as a scientific issue, we try to look at it as a European initiatives and what's going on in the world. And based on our comparison, we assess that the main benefit of organic materials is that we can develop a scalable technology. So we are talking about something that we can integrate in other platforms. Yes, we have some issues with stability and brightness. It's not our main strong part. Cosmos space is something we probably won't go, but we can do a lot of here on the spot. And especially here in Europe about developing technology. So we are talking about wet coating systems to deposit in our sources on chips, and also to create this, all the necessary waveguide structures around. So, very cool, very nice. Why don't we have like all that backed up and here on the table as a ready product? Because sadly, the road from science to application is not just a one step forward, but it's like a multitude of smaller steps that we need to do. We need to do a lot of material research. We need to do single photon source fabrication and establish how we can fabricate them. We need to do the integration steps. So it's not about that just we have a glass substrate where somewhere we have a single photon source. We want it to be aligned with our structures that we can use it for some functionalities. Control, that we can actually like make it emit when we want it to emit, and then, only then, when we have all this pipeline ready and going and very nice, we can finally start to talk about applications. So where are we now? So what's done? We are not the first ones that are thinking about organic material usage for quantum light sources. This is something that's already done a lot of work in literature. There's one molecule that's already very popular, the DBT. It's a very, very planar molecule. It has very nice properties regarding like high photostability, high quantum yield, zero phonon lines. But just to give like a more intuitive idea why this is a good molecule. The main issue with quantum light sources for organic materials is that, like, in a lot of cases with organic materials, when you have a complex system, it has a lot of free space and a lot of like freedom to vibrate and rotate. So it can, whenever you give it energy, it can dissipate through heats, through vibrations and rotations and things like that. DBT is very, very planar. It's basically, you can imagine like a sheet. So it has very few freedoms where you can dissipate energy through vibrations. And when you look at like other alternatives for quantum light sources, usually they all are very, very planar molecules, as they are just very, very good at converting your energy to single photons because it cannot dissipate. And yeah, overall, this shows a great potential for integrated photonics. There is already some work done with coupling these sources with waveguides. So I would say we are currently, overall in the world, the technology development is to the integration part. I need to stress out here one essential thing. This integration is not, in most cases, is not like that you have a ready chip and you can place your source on the chip where you need it. In a lot of cases is you first fabricate your single photon source, and then it's much easier to build your photonic chip around it. So you place a micro lens on top of it, or you try to draw a waveguide next to it. It's cool, it works for scientific demonstrations, but if we actually are thinking about scalable technology that can fabricate something in the mass, we probably need to work on really placing the source where we need it. Every molecule is a single source by itself, so we need to work in the single molecule level. It's quite difficult to manipulate a single molecule, not easy. So what's actually done is usually you have a crystal, so basically you mix it, your single photon source in another material, host material, and in this case mostly used anthracene, which basically puts, like, it can fold around your molecule, create a very rigid structure, press it between, and then you, diluting it enough, you can get a crystal where you have a single molecule as a source. And then you work with this crystal as a single photon source. So in Latvia, in the Institute of Solid State Physics, we are working here together with Riga Technical University, with chemists from their size, on synthesis of new single photon emitters, developing single photon source fabrication and characterization, and this is the place where our university is helping us a lot to understand how we can correctly test them and learn from their experience. Of course, the final goal of this whole project is to get to the point where we have also a possibility to heterogeneously integrate it in other photonic platforms. But currently, we are here. We are working with synthesis, we are working with characterization, and here our main idea is basically we are taking already known materials and we are changing the hydrogen atoms with deuterium, and the idea is quite simple. Again, the whole concept is to limit the vibrations. So what do? You basically put something, if you have like a paper sheet and you want to hold it in place, put something heavy at the ends of it so it keeps rigid. Basically, that's the deuterium atoms. It's keeping the molecule more rigid and allowing it to become even more efficient single photon source emitter. So, next part, entangled photon sources. So here we are transitioning from a source that gives us one photon to a magical thing that gives us two photons. Not much scalability, but still a very essential thing. But there's a trick about these two photons, and the main thing is that the quantum states are interconnected. So basically determines each other once. There are a lot of ways how to generate these pairs. We are focusing on nonlinear optics that allows basically we can excite a system so it would emit two photons with bit different wavelengths. And it's, in my sense, entanglement is still something of a bit of a magical thing. I really like this one paper where they were studying like this phase correlation for entangled photons and basically got this very nice yin-yang science that kind of gives me a personal feeling that it's still a bit of a magic what's going on. Because how they communicate, I have no idea. But okay, again, like why organic materials? Very simple, efficiency. So when we compare to already existing platforms, we today had talks about different materials that can be used for frequency comms and so on. Organic materials can give us 10 or even 2 magnitudes of, so single or 2 orders of magnitude higher efficiency. Which translates in practice less energy for the source to work. Of course, there's some limitations. First of all, we cannot create structures from just this pure organic material. We need to dilute it in a polymer, but still we have good results that we can get like 10–30% of our material in, and still we could get like at least a magnitude of order higher efficiency. The other thing is spectral properties, so the higher values are for organic materials at very specific wavelengths corresponding to their absorbance. But this, again, we can working together with Greek Technical University, we can very well get around by just synthesizing a multitude of different organic compounds with different spectral to really tune our response at very specific wavelengths. So, again, I'm very sorry, there's a little bit of a mistake, but yeah, entangled photon sources. So what we are doing regarding this, again, here, as we have already done a lot of work regarding material characterization, we are looking at some synthesis of new materials, but we are really focusing on integration of our materials with other platforms. And here we are working together with Trento University. We had recently very nice first tests of our chips to just see if they are fitting their experimental setup and got nice results. Our hope with the synthesis is we kind of want to push a limit, which is possible, of this nonlinear efficiency to get 3 orders of magnitude higher compared to silicon carbide and nitride. Mainly because that would allow us for smaller dilution of, a higher dilution of our material in the host polymer and would allow for easier manufacturing. Regarding the manufacturing part, we have multitude of ways how we can structure and create our entangled photon sources. I will touch on 2. So first is direct writing with electron beam lithography that is available for us in solid-state physics. And we have had good results about creating the structures, and now we are just planning the first test experiments at Trento University to see whether they work. Another thing which is very interesting and I think quite novel approach is trying to print our materials into trenches with the idea to really integrate our materials into other platforms, because this is the way how we can just, in any kind of other platform, we can just create a trench, we can fill it with our material, and we have a local element in other platforms. So just to have a conclusion, overall, we are quite actively working on both of these fields. And currently, we are still focusing a lot of material synthesis and this focus on integration with like element fabrication, device demonstration. But I think like already our current established gotten results gives us a good indication to, we believe that the main motivation for this is this could be a scalable technology if we are talking about something to fabricate here in Europe for not a lot of, we don't need like billions to establish a manufacturing, much lower costs, and this is especially when we talk about Baltics, so we can do it locally here with not like gigantic investment. With that, thank you for your attention.